Imagine standing at the edge of a place so deep that if Mount Everest were dropped into it, the mountain would disappear like a coin down a wishing well. No echo, no splash, just silence. The Mariana Trench is not just deep, it is aggressively deep, the kind of deep that feels personal. Like the ocean woke up one day and said, "Let's see how confident humans really are." Sunlight never reaches this place. Sound behaves strangely. Time feels slower. And the rules we rely on up here at the surface start quietly packing their bags. If this calm dive into what we may have misunderstood about the Mariana Trench helps you relax tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening, so this slow science can reach more people who fall asleep to the deep ocean's mysteries. The trench sits in the western Pacific Ocean, a long, curving scar in Earth's crust that stretches farther than many countries. It is not dramatic in the way volcanoes are dramatic. There is no fire, no explosion, no cinematic lava fountains. Instead, it is dramatic in a more unsettling way. It is a vast, crushing absence, a place defined by what it takes away: light, warmth, familiarity, and certainty. And that is exactly why scientists are beginning to realize something uncomfortable. The more we learn about the Mariana Trench, the more it seems that some of our most confident ideas may be standing on very thin ground. Or, more accurately, very thin steel hulls. We like to think of science as a steady march toward truth, a clean line moving forward with each new discovery. But the trench does not care about neat lines. It is a reminder that knowledge is often provisional, especially when the environment actively tries to destroy your measuring tools. Down there, pressure stacks up relentlessly. Every meter adds more force. Every descent is a negotiation with physics. Materials bend. Electronics misbehave. Sensors whisper lies through distortion. It is not that the trench is hiding secrets on purpose. It is that it exists under conditions so extreme that even observing it feels like an intrusion. There is something humbling about that. Humans have walked on the moon. We have robots on Mars. We can split atoms and edit genes. And yet, a place on our own planet remains largely unvisited, barely understood, and deeply suspicious of our presence. The Mariana Trench is not impressed by our resumes. It does not care how many degrees we have or how advanced our instruments claim to be. Down there, everything is put to the test, including our assumptions about how the natural world should behave. For a long time, the trench was treated as a kind of footnote. Yes, it was deep. Yes, it was extreme. But it was often framed as a simple extension of the ocean above it, just darker, colder, and more pressured, like the basement of a familiar house. Turns out, it is less like a basement, and more like discovering that your house has a secret underground city with its own laws, culture, and very questionable plumbing. The deeper scientists look, the more they realize that the trench is not merely an endpoint. It is an environment shaped by forces that rarely interact anywhere else on Earth. This realization has sparked a growing unease in the scientific community, and it is not the bad kind of unease. It is the exciting kind. The kind that makes researchers lean forward instead of back. Because if some of our ideas about the trench are wrong, then what else might need revision? If the deepest part of our own planet does not behave the way we expect, then perhaps our models are incomplete. Perhaps our mental maps are missing entire dimensions. The trench also forces us to confront an uncomfortable truth about exploration itself. Much of what we know about extreme environments comes from brief encounters, short visits, fleeting glimpses, a few samples scooped up and hurried back to safety. Imagine trying to understand a rainforest by parachuting in for 10 minutes, grabbing a handful of leaves, and declaring the ecosystem solved. That is, in many ways, what we have been doing with the Mariana Trench. And the trench, in response, has been quietly smirking. There is a strange poetry to the idea that the most alien environment humans have encountered is not on a distant planet, but right here, beneath our own waves. The Mariana Trench does not roar or threaten. It simply exists, applying pressure, bending expectations, and reminding us that certainty is a surface luxury. Down there, nothing is simple, nothing is guaranteed, and nothing behaves just because we want it to. As we begin this journey, the goal is not to marvel at how deep the trench is, but to question how well we actually understand it. Because the real mystery is not just what lives there or how deep it goes. The real mystery is how often the trench has already told us we were wrong and how long it took us to listen. Long before scientists had sleek submersibles and glowing screens full of data, the deep ocean was approached with a mix of curiosity, optimism, and equipment that now feels charmingly unqualified for the job. Early ocean explorers knew the sea was deep, but how deep was a question answered with ropes, weights, and a lot of patience. The process was simple in theory. Lower a line until it hit bottom, then measure how much rope was gone. The process was also wildly impractical once the rope kept going, and going, and going, and still hadn't hit anything. Somewhere along the way, the ocean politely declined to cooperate. These early measurements were less about precision and more about endurance. Ropes stretched. Currents pulled lines sideways, weights drifted. Sometimes the rope snapped, and the ocean kept the evidence. The result was depth estimates that varied dramatically depending on weather, equipment, and how optimistic the crew felt that day. It was a bit like trying to measure the height of a skyscraper using a piece of yarn in a windstorm while standing on a moving sidewalk. Not ideal, but it was all anyone had. Everything changed when sound entered the picture. Instead of physically touching the bottom, scientists realized they could listen for it. Echo sounding worked by sending a sound pulse downward and timing how long it took to bounce back. Knowing how fast sound travels through seawater allowed them to turn that delay into a depth estimate. It was a brilliant leap forward, but the earliest versions were crude. These devices sent out loud pings and waited, like someone yelling, "Hello?" into a canyon and counting Mississippi, seconds before hearing a faint reply. The first echo sounders did not produce clean images or detailed maps. They generated numbers, often scribbled down by hand, while ships rolled and engines hummed. The sound waves spread out, scattered, and reflected off more than just the seafloor. Layers of water, with different densities, could bend or slow the signal. Slopes could deflect it. Trenches, with their steep walls and complex shapes, were particularly uncooperative. The abyss did not give straight answers. It gave echoes with opinions. When survey ships passed over what would later be known as the Mariana Trench, the readings were startling. The numbers coming back suggested depths far beyond what anyone expected. At first, there was skepticism. Instruments were blamed. Calibration was questioned. After all, if your tool suddenly claims the ocean is far deeper than anything measured before, the polite scientific response is, "Are you sure your machine isn't having a bad day?" Multiple passes were made. Different ships took readings. The deep numbers persisted, stubborn and unbothered by disbelief. Mapping, however, was another challenge entirely. Early echo sounding produced single lines of data beneath a moving ship. Imagine trying to draw a detailed map of a mountain range by driving over it once, and only recording the elevation directly under your tires. Large gaps filled the space between measurements. Interpolation became an art form. Scientists connected dots with educated guesses, smoothing out features that might not have been smooth at all. The trench began to emerge on maps as a long depression, but its true shape remained elusive, like a shadow seen through fog. Another limitation was directionality. Sound does not travel in a perfectly narrow beam unless carefully controlled, and early systems were anything but careful. Pings spread out, meaning echoes could come back from the sides of the trench rather than the deepest point directly below. This could make the seafloor appear shallower than it really was, or sometimes deeper, depending on geometry. The ocean floor was essentially playing acoustic tricks, and scientists were trying to interpret them without knowing the punchline. Despite these challenges, echo sounding revolutionized oceanography. For the first time, vast areas of the seafloor could be surveyed in a fraction of the time older methods required. Patterns emerged. Trenches, ridges, and plains took shape on paper. The Mariana Trench transitioned from rumour to recognised feature. Its depth no longer a guess, but a measured, if still uncertain, reality. It was a breakthrough born not of perfection, but of persistence. There is something endearing about those early maps. They are rough, cautious, and filled with quiet question marks. They represent humanity's first serious attempt to listen to the deep instead of poking it with a stick. And while those early echo sounders were far from flawless, they opened the door to everything that followed. They taught scientists that the ocean could be measured indirectly, that sound could reveal landscapes hidden under kilometers of water, and that the deep was far more dramatic than anyone had imagined. In hindsight, it is easy to see their limitations. But without those primitive shouts into the abyss, we would not even know which questions to ask today. The Mariana Trench entered human awareness not with a dramatic discovery moment, but with a series of puzzled looks at instruments that kept insisting, "No, really, it's that deep." And sometimes the first step toward understanding is simply believing the echo. You would think that by now we could agree on how deep the deepest place on Earth actually is. Pick a number, carve it into scientific stone, move on. And yet, the reported depth of the Mariana Trench has changed repeatedly over the decades. Not by a few centimeters, but by meters. Enough to make headlines. Enough to make scientists politely argue at conferences while pretending they are not arguing. The trench is not playing tricks on us out of spite. The issue is that measuring deepest turns out to be far more complicated than it sounds. The first problem is deciding what exactly depth means. Depth is not measured from the center of the Earth or some cosmic reference point. It is measured from sea level, and sea level is not a flat, static surface. It is a restless, uneven, constantly shifting boundary influenced by tides, currents, temperature, and even the shape of Earth's gravity field. The ocean surface bulges slightly in places where gravity is stronger and dips where it is weaker. This invisible, lumpy surface is known to geophysicists as the geoid, and it means that 0 meters is already a moving target before you even start measuring downward. Then there are tides. Even in the open ocean, far from shorelines, tides raise and lower the sea surface by measurable amounts. When a depth measurement is taken, it captures a moment in time. If another measurement is taken at a different tidal phase, the numbers will differ unless carefully corrected. Early surveys did not always have the luxury of precise tidal models, especially in remote regions of the Pacific. Comparing old and new measurements is like comparing heights taken once, with shoes on and once barefoot. except the shoes are made of water and never stop changing. Another factor is the shape of the seafloor itself. The deepest point of the Mariana Trench, often referred to as Challenger Deep, is not a single, perfectly defined hole. It is a region with slopes, ridges, and small depressions. Depending on exactly where an instrument passes, it may record a slightly different maximum depth. Think of it less like a single pit and more like a crumpled blanket with several low spots. Declaring one point the deepest depends on resolution, coverage, and a bit of interpretation. Technology has improved dramatically over time, and with each improvement comes a reassessment of previous results. New instruments can resolve finer details, distinguishing features that older systems blurred together. When higher resolution data reveals a spot slightly deeper than what was previously identified, the record changes. This does not mean earlier scientists were wrong. It means they were working with a blurrier picture. It is the difference between using a flashlight and using a microscope, except the microscope is dangling several kilometers above the ocean floor. There is also the issue of sound speed in seawater, which depends on temperature, salinity, and pressure. Small uncertainties in how fast sound travels translate into depth differences when dealing with extreme distances. Modern measurements use detailed profiles of the water column to refine these calculations, while older surveys relied on generalized assumptions. Over long distances, even tiny errors add up. When you are measuring something that is nearly 11 kilometers deep, a fraction of a percent matters. Earth itself adds another layer of complication. The planet's crust is not rigid. It flexes under the weight of the ocean. Changes in mass, such as shifting water loads or tectonic forces, can cause subtle vertical movements over time. These movements are slow and small, but when scientists are chasing precision, they become relevant. The deepest point on Earth is not nailed in place. It is more like a very patient elevator, moving so slowly that only long-term measurements notice. Sediments also play a role. Fine material can slide down slope and accumulate in low areas, filling them in slightly. Elsewhere, slumping can expose deeper underlying surfaces. These processes do not happen overnight, but over years and decades they can alter the micro-topography of the trench floor. The Mariana Trench is not a static monument. It is a dynamic landscape, constantly adjusted by gravity and time. Finally, there is the human element. Different research teams use different methodologies, reference models, and data processing techniques. Each decision introduces subtle variations. Scientists are careful to quantify uncertainty, but headlines love single numbers. Deepest point measured at X meters sounds definitive, even when the scientists involved would happily explain that X comes with a margin of error and several footnotes. So the depth keeps changing, not because the trench is unreliable, but because our measurements are becoming more honest. Each new number reflects a better understanding of what it even means to measure depth on a living, breathing planet. The Mariana Trench is not getting deeper or shallower in any dramatic way. We are simply getting better at asking the question. And like that stubborn child on the height chart, the trench keeps reminding us that growth in science often shows up as revision. Pressure is the Mariana Trench's signature move. Not darkness, not cold. Pressure. It is the constant, invisible force that defines everything that exists there. At the surface, our bodies live under one atmosphere of pressure, something we never notice because we evolved inside it, but descend into the ocean and pressure increases relentlessly. By the time you reach the deepest parts of the trench, the force pressing in from all directions is more than 1,000 times what we experience at sea level. It is not dramatic in the way an explosion is dramatic. It is quiet, patient, and absolute. To understand what that means, imagine stacking elephants, not side by side, but on top of each other. Now imagine stacking enough elephants to fill a small city. That is roughly the kind of force acting on every square inch down there. Steel hulls creak, glass shatters unless specially engineered, air pockets vanish, and biology, which we tend to think of as fragile, somehow keeps going. This alone makes pressure one of the most fascinating aspects of trench science, and also one of the hardest to replicate convincingly in a laboratory. In labs, pressure is usually simulated using thick-walled chambers, often made of steel or specialized alloys. These chambers can reach impressive pressures, and they are invaluable tools, but they simplify reality in subtle ways. Real deep-sea pressure is perfectly uniform, pressing from all directions equally. Lab systems sometimes introduce gradients, tiny inconsistencies, or mechanical constraints that living organisms never encounter in the open ocean. It is the difference between being hugged tightly on all sides versus being squeezed in a very expensive vice. Another challenge is scale. Pressure chambers are small, they have to be. Engineering something large enough to hold extreme pressure without failing is a monumental task. As a result, experiments are often conducted on small samples, isolated cells, or tiny organisms. This makes it difficult to study how complex systems behave under pressure. Tissues interact differently than individual cells. Organisms respond as wholes, not as collections of parts. Studying pressure effects in isolation risks missing how everything works together when there is no escape in any direction. Time is another overlooked factor. Many laboratory experiments expose samples to high pressure for hours or days. In the Mariana Trench, pressure is not a temporary condition. It is a lifelong reality. Every chemical reaction, every cellular process, every structural component evolved under that constant load. Short-term exposure can trigger stress responses that are irrelevant to organisms adapted to live there permanently. It is like studying human health by locking someone in a wind tunnel for an afternoon and calling it climate research. Pressure also interacts with other physical properties in ways that are difficult to reproduce simultaneously. Under extreme pressure, molecules pack closer together. Chemical bonds behave differently. Proteins can fold into shapes that would be unstable at the surface. Water itself becomes slightly more compressible, subtly altering how substances dissolve and react. Laboratories often study these effects one at a time, but in the trench, they all happen at once, all the time, with no off switch. Even materials science struggles to keep up. Metals, ceramics, and composites can behave unpredictably under sustained high pressure. Microfractures form, fatigue accumulates. Components that perform flawlessly in testing may fail after prolonged exposure. This is not because the tests are bad, but because they cannot fully replicate the complexity of real conditions. Pressure in the trench is not just high. It is persistent, inescapable, and paired with an environment that offers no forgiveness for mistakes. Biology adds another layer of complexity. Many deep-sea organisms rely on pressure to maintain their structural integrity. Remove that pressure, and their tissues lose shape, their chemistry changes, and their normal functions collapse. Studying them at lower pressures is not just inconvenient, It fundamentally alters what they are. Laboratory simulations can maintain pressure, but often at the cost of observation, manipulation, or long-term stability. The very act of studying pressure-adapted life can distort the phenomenon being studied. There is also a psychological trap in simulations. When researchers can control variables, it creates a sense of mastery. But the trench does not operate under controlled conditions. Pressure there is not an isolated variable to be dialed up and down. It is the background against which everything else occurs. By isolating it in experiments, we risk misunderstanding its role. Pressure is not just another factor. It is the stage, the lighting, and the gravity holding the entire performance together. This is why some assumptions based on laboratory results may be incomplete or misleading. It is not that the experiments are wrong. It is that they are necessarily simplified. They capture slices of reality, not the full experience. The Mariana Trench exists at the extreme edge of what matter, life, and technology can tolerate. And recreating that edge inside a building on land will always involve compromise. Pressure, in the end, is a reminder that some environments cannot be fully domesticated for study. They resist being scaled down. They demand respect. And the Mariana Trench, applying its 1,000 atmospheres without complaint, continues to remind us that understanding a place shaped by such force requires more than strong materials. It requires humility. If pressure is the Mariana Trench's signature move, temperature is its subtle plot twist. Most people imagine the deepest ocean as a uniformly frozen abyss, a kind of liquid Antarctica where everything is equally cold, equally still, and equally miserable. And yes, it is cold down there, brutally so by human standards. But the mistake lies in assuming that cold means simple. In the Mariana Trench, temperature is not a flat line. It is a patchwork, and those tiny variations matter far more than you might expect. At great depths, sunlight has long since vanished, so there is no daily warming cycle, no seasons in the familiar sense. The water is chilled by contact with polar currents and by the sheer absence of heat input. Average temperatures hover just above freezing. But average is doing a lot of work in that sentence. Even differences of a few tenths of a degree can change how chemicals behave, how fluids move, and how living systems function. In an environment already pushed to extremes, small changes stop being small. One reason temperature varies is water movement. The deep ocean is not motionless. It circulates slowly, driven by global currents that sink, spread, and creep along the seafloor. As these water masses move, they carry distinct thermal signatures, shaped by where they formed and how long they have been isolated from the surface. When different deep currents intersect within the trench, subtle temperature gradients form. They are nearly invisible by surface standards, but in the deep, they are meaningful landmarks. The shape of the trench itself also plays a role. Steep walls, terraces, and depressions influence how water settles and flows. Cold water can pool in certain areas, while slightly warmer water drifts through others. This creates microclimates on the seafloor, zones where conditions differ just enough to favor certain chemical reactions or biological strategies. The trench is less like a uniform freezer and more like a very large, very dark wine cellar with oddly specific temperature preferences. Temperature affects chemistry in ways that are easy to underestimate. Reaction rates slow down as temperatures drop, Some processes that happen readily near the surface become sluggish or nearly stall. Gases dissolve differently. Solubility changes. Certain compounds remain stable far longer than expected. Others behave unpredictably. Models built using surface or shallow water data often fail to account for how chemistry shifts when cold becomes the default state rather than a temporary condition. This has implications for how scientists interpret samples. A chemical signature preserved in the cold depths might reflect processes unfolding over extremely long timescales, not rapid events. Without accounting for temperature's influence, it is easy to misjudge how fast something formed or how active an environment truly is. Cold does not mean inactive. Sometimes it means patient. Biology feels these differences too. Temperature influences metabolism, growth rates, and energy use. In cold environments, life often operates in slow motion. Cells divide more slowly, repairs take longer. Energy is budgeted carefully. But again, tiny differences matter. A fraction of a degree can tip the balance between barely surviving and quietly thriving. Species adapted to one thermal niche may struggle just meters away in slightly colder or warmer water. This creates a mosaic of biological possibilities. Rather than a single, uniform deep-sea community, the trench may host distinct assemblages shaped in part by these subtle thermal gradients. Temperature becomes an invisible boundary, dividing habitats without walls. To us, it all feels equally cold. To organisms that evolved there, those differences are as real as the difference between summer and winter. Temperature also interacts with materials in ways that challenge technology. Cold affects battery performance, sensor accuracy, and mechanical flexibility. Instruments calibrated in controlled conditions may drift when exposed to prolonged cold. Components contract, fluids thicken, timing circuits behave slightly differently. These effects are small, but when precision matters, small errors compound. Data collected without fully accounting for thermal conditions can quietly mislead. There is also a psychological component for scientists. Cold is familiar. We understand it intuitively. We know what freezing feels like. That familiarity can breed overconfidence. It is tempting to assume that cold behaves the same everywhere. That once you know the temperature range, you know the story. The Mariana Trench resists that simplification. Down there, cold is not just a number. It is a controlling factor that shapes everything from molecular interactions to ecosystem structure. Perhaps the most humbling lesson is how close these temperatures are to critical thresholds. A slight change in circulation, a subtle shift in water mass distribution, and conditions could change enough to alter long-standing balances. The trench may appear stable, but its thermal structure is delicately arranged. Our understanding of it rests on measurements that capture snapshots, not lifetimes. In the end, temperature in the Mariana Trench teaches a broader lesson about extremes. When environments push the limits, details stop being details. They become the story. And in a place where being wrong by half a degree can ripple through chemistry, biology, and technology, confidence has to be handled with care. The trench is cold, yes, but it is also nuanced, and it punishes anyone who mistakes simplicity for understanding. If you were asked to design a place where life should not exist, the Mariana Trench would be a strong candidate. No sunlight, crushing pressure, near freezing temperatures, scarce food, and yet, life not only exists there, it does so with a quiet confidence that feels almost disrespectful to everything we were taught in introductory biology. The trench is not teeming in the way a coral reef is teeming, but what lives there plays by a different set of rules. ones written under conditions most organisms never experience. One of the first surprises was simply finding multicellular life at all. For a long time, it was assumed that extreme depth would limit life to simple forms, perhaps bacteria at best. That assumption did not survive contact with reality. Researchers began finding crustaceans, worms, and fish-like creatures that looked oddly familiar and deeply alien at the same time. Their basic body plans made sense, but the details told a different story. As if evolution had taken a familiar template and rewritten it for an environment that actively resists existence. A major rule breaker involves cell membranes. In basic biology, membranes are taught as flexible barriers made of lipids that maintain just the right balance between rigidity and fluidity. Too stiff, and nothing works. Too floppy, and everything leaks. In the trench, pressure pushes molecules together with relentless force. Under such conditions, typical membranes would become too rigid to function. Trench organisms solve this by altering the composition of their membranes, using different lipid structures that remain functional under extreme compression. It is the biological equivalent of wearing a custom-tailored suit to survive being hugged by a planet. Proteins, the workhorses of life, also misbehave under pressure. High pressure can cause proteins to unfold or change shape, destroying their function. Many trench organisms produce pressure-stabilized proteins that maintain their structure where ordinary proteins would fail. These proteins often look similar on paper, but behave very differently in practice. This forces scientists to rethink assumptions about protein stability that were based largely on surface conditions. Biology, it turns out, is deeply context-dependent. Metabolism in the trench also challenges textbook ideas. We often associate life with energy abundance, growth, and reproduction. In the trench, energy is scarce and unpredictable. Many organisms adopt extremely slow metabolic rates. They grow slowly, reproduce infrequently, and waste almost nothing. This is not inefficiency, it is precision. Life down there is optimized for survival, not speed. The usual biological race toward rapid reproduction is replaced by a long, careful marathon, where patience is the winning strategy. Some trench species show unexpected flexibility in diet. Instead of specializing narrowly, they take advantage of whatever organic material becomes available. This can include particles drifting down from above, remains of larger organisms, or material transported by deep currents. These feeding strategies do not fit neatly into surface-based food categories. They are opportunistic, adaptive, and shaped by an environment where meals are unpredictable and every calorie matters. Reproduction itself can look strange. Some organisms invest heavily in fewer offspring, increasing the chances that at least one survives in a harsh environment. Others show adaptations that allow larvae to develop under conditions that would normally be lethal. Developmental timelines can be stretched, with life stages lasting far longer than their shallow water counterparts. These strategies defy the fast-paced life cycles often highlighted in basic biology classes. Even sensory systems challenge expectations. In total darkness, vision is often reduced or absent. But that does not mean these animals are unaware of their surroundings. Many rely on chemical cues, pressure changes, or subtle vibrations to navigate and find food. These senses are rarely emphasized in human-centered biology education, but in the trench, they are primary. Life does not need eyes when the environment provides other ways to perceive reality. Perhaps the most unsettling discovery is how little these organisms resemble our assumptions about fragility. We tend to think of life as delicate, easily disrupted, Trench life is robust in its own way, engineered by evolution to function under constant stress. It is not invincible, but it is astonishingly well adapted. The conditions that would destroy surface organisms are simply normal down there. All of this forces a re-examination of what we mean by habitable. If life can adapt to the Mariana Trench, then the boundaries we draw around where life should or should not exist start to blur. The trench does not just add new species to the tree of life. It reshapes the tree's branches, reminding us that biology is less about universal rules and more about local solutions. In the end, life in the trench feels like a quiet rebellion. It does not announce itself loudly. It does not conform to our expectations. It simply persists, doing biology in ways that make our textbooks look a little overconfident. And perhaps that is the most important lesson it offers. Life is not obligated to make sense to us. The moment a deep-sea organism begins its journey to the surface, physics starts undoing it. What lived comfortably under immense pressure suddenly finds itself in an environment that feels, from its perspective, violently wrong. Tissues expand, gases come out of solution. Structures that relied on external pressure for support lose that support instantly. By the time many organisms reach the surface, they are no longer representative of what they were alive in the trench. They are biological crime scenes. This creates a fundamental problem for science. If the act of observation destroys the subject, how much can we really learn? For decades, much of what scientists knew about deep-sea life came from trawls and dredges that hauled organisms upward through kilometers of water. These methods were efficient at collecting material, but brutal in their consequences. Delicate structures collapsed, internal organs shifted, soft tissues ruptured. What arrived on deck often bore only a vague resemblance to its living form. Pressure-adapted organisms are especially vulnerable because many of their structural features are designed with the assumption that immense pressure is always present. Some lack rigid skeletons entirely, relying instead on the surrounding water to maintain shape. Others have internal fluids, balanced precisely against external pressure. Remove that pressure, and balance turns into chaos. It is not that these animals are weak, they are specialized. They are perfectly built for a world we cannot bring with them. This distortion extends beyond appearance. Biochemical processes change as pressure drops. Proteins may denature. Enzymes may stop working as intended. Chemical gradients that drive cellular processes dissipate. By the time scientists begin examining these organisms, their physiology is no longer operating normally. Measurements taken under these conditions can be misleading, leading to conclusions based on bodies that are, functionally speaking, no longer alive in the way they were meant to be. Even behavior becomes impossible to interpret. A creature adapted to the trench does not swim, feed, or react under surface conditions the way it would in its natural habitat. Observing its movements in a low-pressure tank is like judging a deep-sea fish for not flapping its fins properly, while it is slowly falling apart. The data collected may be accurate in a narrow technical sense, but it fails to capture the reality of life under extreme depth. Preservation methods introduce their own problems. Fixatives can alter tissue structure. Freezing can cause expansion and rupture. Dehydration changes volume and texture. Each step taken to preserve a specimen for study further distances it from its original state. Scientists are left piecing together how an organism might have functioned based on remains that have been fundamentally altered by the journey to the surface. This has led to historical misunderstandings. Early descriptions of deep-sea species often emphasized deformities or odd proportions that were, in hindsight, artifacts of decompression. Some creatures were thought to be gelatinous or amorphous, when, under pressure, they are actually well-defined and structured. The trench did not produce monsters. Our methods did. The challenge has forced innovation. Researchers began developing pressure-retaining devices designed to keep organisms under high pressure during ascent and study. These systems are complex, expensive, and technically demanding, but they offer a more faithful glimpse into trench biology. Even then, maintaining stable conditions long enough to observe natural behavior remains a major hurdle. The deeper the origin, the harder it becomes to preserve the context of life. There is also an ethical dimension. As awareness grows that many deep-sea organisms cannot survive traditional collection methods, scientists must balance the desire for knowledge with the cost of obtaining it. Studying life that cannot be brought to the surface intact pushes research toward in situ observation, where organisms are studied in their natural environment. This shift acknowledges a hard truth. Some environments cannot be meaningfully sampled without loss. The fragility of these creatures outside their world highlights how tightly life can be coupled to its environment. We often think of organisms as self-contained units, capable of being moved and studied anywhere. The Mariana Trench challenges that assumption. Its inhabitants are not portable, they are context-dependent in the deepest sense. Trying to understand trench life by examining surface-recovered specimens is like trying to understand a musical performance by studying a smashed instrument. You might learn something about the materials, but you will miss the music entirely. The deeper lesson is not just about technical difficulty, it is about perspective. To truly understand life in the Mariana Trench, we must meet it on its own terms, in a place where pressure is not an obstacle, but the foundation of existence. When people picture ecosystems, they usually imagine something visible and bustling. Forests layered with leaves and animals. Coral reefs exploding with colour and movement. The Mariana Trench offers none of that visual reassurance. Its ecosystem is quiet, sparse, and spread thin across immense darkness. And that is exactly why understanding its food web has proven so difficult. In the trench, energy does not flow in obvious ways. It trickles, drifts, and occasionally arrives in dramatic, unpredictable pulses. At the surface, food webs often begin with sunlight. Plants capture energy, herbivores eat plants, predators eat herbivores, and so on. In the trench, sunlight is a rumour. Primary production does not happen in the usual way. Instead, most energy arrives from above, in the form of organic debris slowly sinking through the water column. This rain of particles, often called marine snow, is made of dead plankton, waste, and fragments of life from far above. By the time it reaches trench depths, it has been picked over, degraded, and stripped of much of its original energy. This makes the trench a place of extreme scarcity. Food arrives slowly and irregularly. Some days, nothing. Other times, a sudden windfall. Large falls of organic material, such as the remains of big animals, can create temporary oases on the seafloor. These events inject energy into the ecosystem in a way that is rare but transformative. For a time, activity spikes. Organisms converge, nutrients circulate. Then gradually, the feast fades, and the ecosystem returns to its baseline austerity. Because food sources are so patchy, trench ecosystems are shaped by opportunism. Organisms must be flexible, able to exploit whatever appears. This makes mapping the food web incredibly challenging. Traditional categories like predator, scavenger, and detritivore blur. A species might fill multiple roles depending on availability. Who eats whom is not fixed. It is conditional, shifting with circumstance rather than following a tidy diagram. Another complication is scale. Many trench organisms are small, and many interactions happen at microbial or microscopic levels. Bacteria and other microorganisms play a foundational role in breaking down organic material and recycling nutrients. Yet these processes are difficult to observe directly, especially in situ. Without a clear picture of these lower-level interactions, the higher levels of the food web float on uncertainty. It is hard to map the top when the base is half invisible. Sampling bias also distorts our understanding. Scientists tend to notice larger organisms more easily, especially those that appear on cameras or are collected by instruments. Smaller, rarer, or more cryptic species may go undetected, even if they play crucial roles. This creates gaps in the food web that are not just unknown, but unknown unknowns. Entire links may exist that have never been observed, simply because they operate at scales or frequencies we have not yet captured. Energy efficiency is another defining feature. In an environment where food is precious, waste is minimized. Nutrients are reused repeatedly. A single input of organic material can support a cascade of activity as it is consumed, transformed, and consumed again. This recycling blurs the boundaries between producers, consumers, and decomposers. The trench food web is less a pyramid and more a tightly wound knot. The spatial structure of the trench further complicates things. Steep walls, ledges, and depressions create distinct microhabitats. Food may accumulate in some areas, while bypassing others entirely. Organisms living only meters apart may experience vastly different levels of resource availability. This patchiness makes it difficult to generalize findings from one location to the entire trench. What is true in one pocket may be false just down the slope. Temporal variability adds another layer. Because food input is irregular, ecosystem dynamics can change over time. Periods of scarcity may favor certain survival strategies, while rare abundance events temporarily reshape community structure. A snapshot observation captures only one frame in a long, slow movie. Without long-term monitoring, it is easy to misinterpret what is typical versus what is exceptional. All of this leads to an unsettling possibility. Our current models of trench ecosystems may be incomplete not just in detail, but in structure. We may be missing entire pathways of energy flow. There could be interactions that dominate the system, but leave little obvious trace, in an environment so difficult to access. Absence of evidence is a particularly weak form of reassurance. The Mariana Trench ecosystem reminds us that complexity does not require abundance. Even in a place defined by scarcity, life organizes itself into networks of exchange, dependency, and adaptation. Understanding those networks is one of the great challenges of deep-sea science, and the more we look, the more it becomes clear that the trench's food web is not just hard to see. It may be fundamentally different from anything we are used to drawing. It is tempting to imagine the Mariana Trench as a permanent scar in the planet, a feature so deep and dramatic that it must be stable, ancient, and unchanging. But the trench is anything but static. It exists at the edge of massive tectonic forces, where enormous slabs of Earth's crust interact in a slow, grinding dance. The result is a landscape that is continually being modified, not violently in a single moment, but persistently over geological time. The trench forms where one tectonic plate bends and slides beneath another in a process known as subduction. This movement is slow on human timescales, measured in centimeters per year, but it is relentless. As the descending plate plunges into the mantle, it drags sediments, water, and rock with it. The upper plate responds by flexing, cracking, and deforming. The trench is the surface expression of this immense underground motion, a visible crease marking a place where the planet is actively rearranging itself. Earthquakes are the most noticeable symptoms of this process. Stress builds as plates stick and strain against one another. When that stress is finally released, the energy radiates through the surrounding rock. In the region around the Mariana Trench, earthquakes occur at a range of depths, some shallow, others plunging far into the earth. Each event, even when small, has the potential to subtly alter the shape of the trench floor and walls. These changes are rarely dramatic in isolation. A single earthquake may shift sediments, trigger a small landslide, or adjust the angle of a slope. But over time, these incremental changes accumulate. The trench is continuously being reworked, its contours softened in some places and sharpened in others. Sediments cascade downward. Exposed rock faces crumble. What looks like a stable feature on a map is, in reality, a work in progress. One of the most important consequences of this activity is sediment redistribution. Material from the trench walls can slump downward during seismic events, filling depressions and creating new layers. Elsewhere, the movement of the subducting plate can pull material away, exposing deeper structures. This constant rearrangement means that the physical environment experienced by organisms is not fixed. Habitats shift, surfaces change. What was once a stable resting place may become unstable after a seismic episode. These geological dynamics also influence how scientists interpret observations. A depth measured in one survey might differ from another, not only because of measurement technique, but because the seafloor itself has changed. The trench is not a rigid container. It is an active boundary. Treating it as static risks misunderstanding both its structure and its behavior. Tectonic activity also creates pathways for fluids to move through the crust. Cracks and faults formed by stress allow water to circulate deep below the seafloor. This movement can alter rock chemistry and change the physical properties of sediments. Over time, these processes can weaken certain areas, making them more prone to collapse during future earthquakes. The trench becomes a feedback system, where movement begets conditions that encourage more movement. The timescales involved challenge human intuition. A few centimeters per year sounds trivial, but over millions of years, that motion reshapes entire regions. The Mariana Trench we see today is not the trench of the distant past, and it will not be the trench of the future. It migrates, deepens, shallows, and changes form as tectonic forces continue their work. Any attempt to describe it as a single, permanent structure misses this fundamental reality. From a scientific perspective, this dynamism complicates modeling. Geological models often rely on assumptions of equilibrium or steady-state behavior. The trench resists those assumptions. It exists in a constant state of adjustment, responding to forces that operate far below the sea floor. Capturing that complexity requires long-term data and a willingness to accept that today's configuration is only a temporary snapshot. There is also an element of humility in recognizing how small human timescales are compared to geological ones. An earthquake that feels sudden and dramatic is, in the life of the trench, just a brief twitch. The real story is written in countless such twitches, layered over vast stretches of time. The trench is not dramatic because of any single event, but because of persistence. Calling the Mariana Trench a slow-motion geological blender is not exaggeration. It mixes rock, sediment, and structure continuously, driven by forces that do not pause for observation. This has profound implications for how we study it. Data collected at one moment must be understood as provisional, shaped by processes that were active long before and will continue long after. In the end, the trench teaches a lesson about Earth itself. Our planet is not finished. It is not settled. Even its deepest places are still under construction, quietly reminding us that stability is often an illusion created by limited perspective. At the bottom of the Mariana Trench lies a slow archive, built grain by grain over immense spans of time. Sediments settle out of the water column and collect on the seafloor, forming layers that, in theory, preserve a chronological record of events. Each layer tells a story about what was happening in the ocean and on land when it was deposited. In calm, undisturbed settings, sediments can act like pages in a history book. The problem is that the trench does not like quiet libraries. It prefers messy workshops. Sediment arrives in the trench from multiple sources. Fine particles drift down from above, the remnants of biological activity and material eroded from distant continents. Other sediments slide down the steep trench walls, carried by gravity in slow cascades or sudden slumps. Some material arrives through deep currents that funnel particles into low-lying areas. The result is a complex mix, not a single orderly rain of material. When geologists extract sediment cores, they hope to see clear layering with older material at the bottom and younger material on top. Sometimes this expectation is rewarded. Distinct layers appear, each representing a different period. Changes in grain size, composition, or color can indicate shifts in climate, ocean circulation, or biological productivity. These layers can preserve chemical signatures that act as timestamps, allowing scientists to reconstruct aspects of Earth's past. But the Mariana Trench rarely makes things that simple. Its steep slopes and tectonic activity mean sediments are frequently disturbed. Earthquakes can trigger underwater landslides that mix layers together. Slumps can carry older material upward or bury younger material beneath it. What looks like a neat stack of pages may actually be a shuffled deck. Interpreting such records requires caution, patience, and a willingness to admit uncertainty. Even in the absence of dramatic events, slow processes can blur the record. Tiny organisms living in the sediment can burrow and mix layers, a process known as bioturbation. Over long periods, this biological stirring can smear boundaries between layers, blending what were once distinct time markers. In environments with limited oxygen, this effect may be reduced, but it is rarely eliminated entirely. The chemistry of sediments adds another layer of complexity. Elements can migrate after deposition, moving through pore spaces in response to chemical gradients. This can alter the original signal preserved in a layer, making it appear younger or older than it truly is. Without careful analysis, these changes can lead to misinterpretation. The sediment is not lying, but it is rewriting parts of its own story. One of the most valuable aspects of trench sediments is their ability to capture rare events. Major disturbances, such as large earthquakes or rapid mass movements, can leave distinctive signatures. These events may appear as abrupt changes in sediment composition or structure. Identifying and interpreting these signatures can provide insight into the history of tectonic activity in the region. However, distinguishing one event from another, or separating a local disturbance from a regional signal, is not always straightforward. The depth of the trench also influences sediment accumulation rates. In some areas, sediments build up extremely slowly, meaning that even thin layers can represent long periods. In others, rapid deposition can occur following a disturbance. This variability makes it difficult to apply a single timeline across different parts of the trench. Each location has its own history, shaped by local conditions as much as by global trends. Geologists must therefore approach trench sediments with a blend of confidence and humility. Analytical techniques can extract remarkable amounts of information from small samples. Isotopic analyses, mineral identification, and microscopic examination reveal details invisible to the naked eye. But these tools are only as good as the assumptions behind them. In a setting as dynamic as the Mariana Trench, those assumptions are constantly being tested. The temptation is to impose order, to force the sediment record into a neat narrative. But the trench resists that impulse. Its sediments tell stories that overlap, interrupt, and occasionally contradict each other. This does not make them useless. It makes them honest. Earth's history is not a smooth timeline. It is a series of episodes, some gradual, some abrupt, layered atop one another in ways that are not always easy to disentangle. In the end, the sediment layers at the bottom of the Mariana Trench are less like a perfectly kept diary and more like a box of old letters, receipts, and notes tossed together over time. With effort, patterns emerge. Stories can be reconstructed, but the process requires care, skepticism, and an acceptance that some pages will always be missing or out of order. And for geologists, that challenge is part of the appeal. Chemistry, as it is usually taught, assumes a fairly narrow range of conditions: moderate pressure, familiar temperatures, reactions happening in beakers that sit politely on lab benches. The Mariana Trench laughs at this framework. Down there, pressure is not just an environmental factor. It is a dominant force that reshapes how atoms and molecules interact. Under such conditions, chemistry does not merely slow down or speed up, it changes character. At extreme pressure, molecules are forced into closer proximity. Spaces that exist at the surface vanish. Electron clouds overlap in ways they normally would not. This can stabilize molecular arrangements that are unstable under ordinary conditions, while destabilizing those we take for granted. Bonds stretch, compress, or rearrange. Reactions that seem unlikely at the surface may become favorable simply because the molecules involved are physically pressed together. It is chemistry conducted in a crowd with no personal space. One consequence of this is the emergence of pressure-favored reactions. Some chemical pathways that require energy at the surface may proceed spontaneously at depth because the volume change associated with the reaction is negative. In other words, reactions that result in more compact products are encouraged when pressure is high. This subtle principle has profound implications. It means that the trench may host chemical processes that are rare or non-existent elsewhere on Earth. The role of water itself also changes. Under extreme pressure, water molecules pack more tightly, altering properties such as density, viscosity, and solvent behavior. This affects how substances dissolve and how ions move. Reaction rates and equilibria shift. Water remains liquid, but it is not the same water we are used to. Treating it as such risks misunderstanding every reaction that occurs within it. These pressure-driven chemical environments may influence nutrient availability and the cycling of elements. Certain compounds could persist far longer than expected, while others may be rapidly transformed. This has implications for how energy and matter move through the trench environment. Chemical reservoirs may exist that are invisible to surface-based models, quietly storing or releasing substances over long timescales. One of the most intriguing possibilities involves the formation of complex organic molecules. Under the right conditions, pressure can promote reactions that build larger structures from simpler components. This raises questions about the trench as a potential site for chemical synthesis that does not fit neatly into surface-based paradigms. While this does not imply anything mystical, it does suggest that our understanding of where and how complex chemistry can occur is incomplete. Another challenge lies in detection. Many of these reactions leave subtle traces, or their products are unstable once brought to the surface. Sampling and analyzing trench chemistry without altering it is extraordinarily difficult. By the time a sample reaches a laboratory, the pressure context that allowed certain reactions to occur has vanished. Interpreting the results becomes an exercise in reconstruction, piecing together what might have happened based on remnants that no longer behave the same way. Laboratory simulations can replicate aspects of high-pressure chemistry, but they struggle to capture the full complexity of the trench environment. Pressure interacts with temperature, composition, and time in ways that are difficult to scale. Experiments often isolate specific reactions, removing them from the broader chemical network in which they would naturally occur. This is useful, but it risks missing emergent behaviors that arise only when everything happens together. The trench may also host chemical gradients, where conditions change subtly across space. These gradients can drive diffusion, reactions, and transport in ways that are poorly understood. Small differences in pressure or composition can create directional flows of chemicals, shaping the local environment. Mapping these gradients is challenging, but ignoring them oversimplifies a system that thrives on nuance. From a theoretical standpoint, the trench pushes chemistry toward its limits. Models developed under surface conditions must be extended, modified, or sometimes abandoned. Assumptions about ideal behavior break down. Non-linear effects become important. This is uncomfortable territory for neat equations, but fertile ground for discovery. Each unexplained anomaly is an invitation to rethink what is possible. Perhaps the most humbling aspect is how much remains unexplored. The deep-sea chemical environment has been sampled far less extensively than surface waters. Entire classes of reactions may be occurring unnoticed, simply because no one has been able to look closely enough for long enough. The trench is not chemically inert. It is active, dynamic, and operating under rules we are only beginning to appreciate. In the end, chemistry in the Mariana Trench reminds us that the behavior of matter is not fixed. It depends on context. Change the pressure, and molecules change their minds. What seems unlikely becomes inevitable. What seems stable becomes fragile. And in that crowded, high-pressure world at the bottom of the ocean, chemistry reveals a side of itself that surface science rarely sees. When most people think of hydrothermal vents, they imagine towering chimneys, blasting superheated water into the ocean, surrounded by dense communities of life. These images come largely from mid-ocean ridges, where volcanic activity fuels dramatic, easily detectable venting. The Mariana Trench exists in a very different geological setting, and assuming its hydrothermal activity looks the same may be one of our quieter mistakes. In the trench, heat and chemistry may move more subtly, leaving fewer obvious clues. Hydrothermal systems form when seawater penetrates the crust, heats up, reacts with surrounding rock, and then returns to the ocean carrying dissolved chemicals. In subduction zones like the Mariana region, the geological context is complex. Instead of fresh volcanic crust forming and spreading, one plate is being forced beneath another. This process introduces water into deep parts of the Earth and alters the chemistry of the descending plate. The result is not necessarily dramatic venting, but a spectrum of fluid movements that can be difficult to detect. One reason trench-related hydrothermal activity may go unnoticed is scale. The flows may be weaker, more diffuse, or spread out over larger areas rather than concentrated in towering structures. Instead of roaring plumes, there may be gentle seepage, slow chemical exchanges that blend into the background. Traditional detection methods, designed to find strong thermal or chemical anomalies, can easily miss these quieter signals. Pressure plays a key role here. At extreme depths, the boiling point of water rises dramatically. Fluids can become very hot without forming obvious plumes. Temperature differences between venting fluids and surrounding water may be small, especially once mixing occurs. A vent that would be conspicuous in shallower water could be nearly invisible in the trench, its heat quickly absorbed by the cold, dense surroundings. Chemical signals face similar challenges. The trench environment is already chemically distinct, shaped by high pressure and unique water masses. Add hydrothermal fluids to that mix, and distinguishing their contribution becomes difficult. Subtle changes in composition may be the only clues, easily lost amid natural variability. Without precise, sustained measurements, these whispers of chemistry fade into statistical noise. The rocks involved also matter. The descending plate undergoes chemical transformations as it sinks, releasing fluids in stages. Some of these fluids may migrate upward through faults and fractures, interacting with overlying sediments and rock. This process can create chemically altered zones rather than discrete vent sites. The energy and materials are there, but they are distributed in ways that challenge our expectations. This has implications for life. Hydrothermal systems are often associated with ecosystems that rely on chemical energy rather than sunlight. If trench hydrothermal activity is more diffuse, it could support life in ways that are harder to recognize. Instead of dense clusters of organisms around a single vent, there may be widespread, low-level support for microbial communities spread across large areas. Such systems would be easy to overlook, especially if we are searching for dramatic visuals. Another complication is longevity. Some hydrothermal systems may be transient, turning on and off as geological conditions change. Others may persist at low levels for long periods. Capturing these dynamics requires long-term observation, something that is difficult and expensive in the deepest ocean. A brief survey might pass through an active area without noticing anything unusual. There is also the issue of bias. Our mental image of hydrothermal vents is shaped by the most spectacular examples. When we look for similar features in the trench and do not find them, it is tempting to conclude that they are absent. But absence of evidence is not evidence of absence, especially in an environment that dampens signals and hides contrasts. From a scientific perspective, this uncertainty matters. Hydrothermal activity influences chemistry, heat flow, and potentially biological productivity. If we underestimate or mischaracterize it, our models of the trench environment remain incomplete. We risk interpreting the system as more inert than it truly is. Understanding trench hydrothermal activity requires adjusting our expectations It may not announce itself with plumes and chimneys. It may speak softly through small chemical shifts and faint thermal anomalies. Detecting it demands sensitive instruments, patience, and a willingness to listen for whispers rather than shouts. In the end, the possibility that hydrothermal activity in the Mariana Trench is hiding in plain sight is a reminder of how perception shapes understanding. When we expect fireworks, we miss the glow of embers. And in the deepest parts of the ocean, where extremes smooth out contrasts, those embers may be doing far more work than we realize. Modern oceanography is built on the quiet assumption that our tools will behave themselves. Sensors are calibrated, systems are tested, software is validated. Then the Mariana Trench enters the conversation and politely dismantles that confidence. At extreme depth, technology does not merely operate at the edge of its specifications. It exists beyond the conditions most engineers ever expected to encounter. The result is a steady stream of small failures, subtle distortions, and outright refusals to cooperate. Pressure is the most obvious adversary. Electronic housings must withstand forces that try to crush them uniformly from every direction. Even tiny imperfections in seals can become catastrophic. A minuscule leak that would be irrelevant at the surface can become a fatal flaw under immense pressure. Materials that perform flawlessly in laboratory tests may behave differently after prolonged exposure, as microcracks grow and components deform. The ocean does not need a dramatic weakness. It is happy to exploit the smallest one. Sensors themselves face unique challenges. Many are designed to measure physical or chemical properties under assumptions that break down at extreme depth. Pressure can alter sensor response in ways that are difficult to predict. Calibration curves derived at lower pressures may no longer apply. The sensor may still produce numbers, but those numbers may quietly drift away from reality. The most dangerous data is not obviously wrong. It is almost right. Temperature compounds these issues. Cold affects electronics, changing resistance, slowing response times, and altering signal strength. Batteries lose efficiency. Timing circuits drift. Even fiber optics can behave differently under combined cold and pressure. Engineers can compensate for some of these effects, but interactions between variables are difficult to model perfectly. The trench creates conditions where small mismatches stack up. Mechanical systems struggle too. Moving parts face increased friction as lubricants thicken or behave unpredictably. Materials that flex easily at the surface may become brittle. Actuators designed for precision may lose accuracy. When a robotic arm misjudges a movement by a small amount at depth, recovery is not always possible. There is no gentle reset button several kilometers below the surface. Communication is another hurdle. Radio waves do not travel well through seawater, forcing reliance on acoustic signals. These signals can be distorted by the complex physical properties of deep water. Noise, reflections, and absorption degrade clarity. Commands sent to deep-sea vehicles may arrive delayed or altered. Data sent back may be incomplete or corrupted. It is a conversation conducted through a medium that actively resists cooperation. Even when systems survive physically, interpreting their data is not straightforward. Extreme conditions can introduce biases that are difficult to identify. A reading may reflect not just the environment, but the instrument's response to that environment. Distinguishing between signal and artifact requires careful analysis and often multiple lines of evidence. One sensor alone is rarely enough. Redundancy becomes essential, but redundancy adds complexity, weight, and potential points of failure. Time exacerbates all of this. Short missions may succeed where long deployments fail. Materials fatigue, seals degrade, sensors drift. The longer a system remains at depth, the more likely it is to encounter an unanticipated issue. Yet, long-term data is exactly what scientists need to understand deep-sea processes. This creates a tension between ambition and reliability. The trench demands patience, but it punishes prolonged presence. Human expectations also play a role. We tend to trust numbers produced by machines, especially when they come with decimal points. But in the trench, precision does not always equal accuracy. A highly precise measurement can still be systematically wrong if the underlying assumptions no longer hold. Recognizing this requires humility and constant validation, qualities that are harder to maintain when the environment is so inaccessible. Failures in the trench are expensive, not just financially, but scientifically. Lost instruments mean lost opportunities. A failed mission may represent years of planning and a rare chance to collect data. This pressure can influence decisions, sometimes encouraging conservative designs that limit what can be measured. The trench becomes not just a physical challenge, but a strategic one. Despite all this, technology continues to advance. Each failure teaches lessons. Designs improve. Materials evolve. Engineers adapt. But progress is incremental, and the trench remains ahead of us, waiting to reveal the next weakness. It is not hostile, exactly. It is simply indifferent. The struggle of technology in the Mariana Trench serves as a reminder that exploration is not just about curiosity. It is about negotiation with an environment that does not care about our goals. Machines, like humans, have limits. And when the ocean presses back with thousands of atmospheres, even our best tools are reminded that confidence must be earned, one successful descent at a time. For most of modern history, the Mariana Trench was imagined as the ultimate untouched place. Too deep to reach, too remote to affect, sealed off from the mess of human activity by kilometers of water. It was the ocean's equivalent of a locked vault. Then scientists started finding our fingerprints at the bottom. Not metaphorical fingerprints, literal ones, in the form of plastics, synthetic chemicals, and human-made debris resting quietly in the deepest environment on Earth. Plastic is the most visible intruder. Bags, fibers, fragments, and microplastics have been found in trench sediments and even inside organisms. These materials do not sink quickly by default. Many are buoyant. They reach the trench through a long, complex journey of degradation, biofouling, and transport by currents. Over time, plastics become colonized by microorganisms, weighed down by biological growth, and pulled into the deep. What begins as floating trash can end as a permanent resident of the abyss. The presence of plastics in the trench forces a reassessment of how connected the ocean truly is. There is no sharp boundary between surface and depth. Material moves vertically and horizontally through processes we are only beginning to map. The trench is not a sealed chamber. It is part of a global circulation system that links coastlines, open oceans, and the deepest seafloor. If something enters that system, it has a chance, however small, of ending up at the bottom. Chemical pollution tells a similar story, but one that is harder to see. Persistent organic pollutants, industrial compounds, and synthetic chemicals have been detected in trench environments. These substances are designed to be stable, which means they resist breakdown. Once they enter the ocean, they can travel vast distances and persist for decades. Some attach to particles that sink, others accumulate in organisms and move through food webs. By the time they reach the trench, they may be diluted, but they are not gone. The deep sea was once thought to be protected by distance and depth. Pollution has proven that assumption wrong. The processes that carry nutrients and energy to the trench also carry contaminants. This creates an uncomfortable realization. There is no true away in the ocean. Disposal does not equal disappearance. The trench becomes a final collection point, a place where long-lived materials settle and remain. For organisms living there, this introduces new variables into an already extreme environment. Plastics can act as physical hazards, entangling or obstructing feeding. Microplastics can be ingested, potentially interfering with digestion or transporting chemicals into tissues. Synthetic compounds may disrupt biological processes in ways that are difficult to predict, especially in organisms adapted to stable, low-input conditions. Studying these effects is challenging. Concentrations of pollutants are often low, but the trench environment magnifies the importance of small changes. Long-lived species with slow metabolisms may accumulate contaminants over extended periods. Effects may be subtle, emerging only over long timescales. Detecting causation in such a remote and complex system is a scientific puzzle with many missing pieces. The discovery of pollution in the trench also challenges ethical assumptions about human impact. It is one thing to damage environments we actively use. It is another to affect places we cannot even reach easily. The trench has become a symbol, not of remoteness, but of reach. Our influence extends farther than our presence. This realization has shifted how scientists think about isolation. Physical distance does not guarantee separation. The ocean's circulation connects everything from surface gyres to abyssal plains. The trench is downstream of global activity. What enters the ocean anywhere can eventually arrive there. There is also a psychological impact. Finding trash at the deepest point on Earth feels like a violation of expectations. The trench was supposed to be different, cleaner, untouched. Its contamination forces a confrontation with the scale of human influence. It reframes pollution not as a local problem, but as a planetary one. Importantly, this does not mean the trench is ruined. It means it is vulnerable. Vulnerable in ways we did not anticipate, and vulnerable on timescales that extend far beyond human lifetimes. The materials accumulating there may persist for centuries, long after their sources are forgotten. In the end, pollution in the Mariana Trench is not just an environmental issue, it is a conceptual one. It dismantles the comforting idea that some places are beyond our reach. The trench is deep, dark, and distant, but it is not disconnected. And in finding our debris at the bottom of the world, we are forced to admit that isolation in the ocean is an illusion we can no longer afford to believe. The Mariana Trench feels vast when described on a map, but it becomes even more intimidating when considered as a research target. It stretches for thousands of kilometers, varies dramatically in depth and shape, and contains countless microhabitats. And yet, our direct observations of it come from an astonishingly small number of visits. A few dives, a few camera drops, a few samples. From this, we attempt to build an understanding of one of the most extreme environments on Earth, It is an effort both admirable and deeply incomplete. Sampling in the trench is constrained by cost, logistics, and risk. Each mission requires specialized vessels, advanced technology, and careful planning. Opportunities are rare. When a dive happens, it must accomplish many goals in a short window. This creates a bias toward efficiency over exploration. Instruments are deployed where they are expected to yield results, not necessarily where the most interesting unknowns might be hiding. The trench is filtered through practical decision-making long before any data is collected. This leads to spatial bias. Certain regions are sampled repeatedly because they are accessible or historically significant. Other areas remain untouched. The trench is not uniform, but our data coverage often treats it as if it were. Conclusions drawn from one location are sometimes generalized to the entire system, even though conditions may vary significantly along its length and depth. This is not careless science. It is the unavoidable consequence of limited access. Temporal bias compounds the problem. Most observations capture brief moments in time. A dive might last hours. A deployment might span days. But the trench operates on timescales that extend far beyond that. Processes unfold slowly. Conditions change subtly. Rare events may dominate long-term dynamics, but occur infrequently. A short observation window may miss these entirely, leading to an incomplete or misleading picture of what is typical. There is also the issue of observer effect. The presence of equipment can influence what is observed. Lights attract or repel organisms. Physical disturbance alters the seafloor. Sampling removes material from the system. Each interaction, however minor, changes the environment being studied. In a place where recovery may take a long time, these effects matter. The rarity of observations also affects interpretation. When data points are few, each one carries disproportionate weight. An unusual finding may be interpreted as representative. A lack of observation may be mistaken for absence. Statistical confidence is difficult to achieve when sample sizes are tiny. Scientists are aware of this, but the temptation to draw conclusions remains strong, especially when data is hard-won. Another challenge is methodological diversity. Different missions use different tools, techniques, and analytical frameworks. Comparing results across studies can be difficult. Variations in methods introduce uncertainty that is hard to quantify. When only a handful of data sets exist, reconciling differences becomes a major challenge. Disagreements may reflect methodological quirks rather than true environmental variation. Limited sampling also shapes research questions. Scientists tend to ask questions that can be answered with the tools and time available. This can narrow the scope of inquiry, leaving broader or more speculative questions unexplored. The trench becomes defined by what we can measure, not necessarily by what is most important or interesting. This skewed perspective can influence theory. Models built on sparse data may fit existing observations well, but fail to capture unobserved complexity. As new data emerges, these models must be revised, sometimes dramatically. This cycle of confidence and correction is a natural part of science. But in the trench, it happens slowly, due to the scarcity of new observations. There is also an emotional dimension. Each dive carries the weight of expectation. Discoveries feel monumental because they are rare. This can amplify their perceived significance. The trench becomes a place of highlights rather than a continuous system. We see moments, not narratives. Recognizing these limitations is not an admission of failure. It is an acknowledgement of reality. The Mariana Trench is difficult to study, and progress will be incremental. Long-term, sustained observation is needed to build a more accurate picture, but achieving that requires resources, commitment, and patience. In the meantime, scientists must balance curiosity with caution. Conclusions must remain provisional. Confidence must be tempered. The trench does not reveal itself easily, and it resists being summarized after a few brief encounters. Judging it based on limited sampling is inevitable, but understanding its limits is essential. The movie is long, complex, and still playing. We have seen only the trailer. For all the confidence that sometimes surrounds scientific descriptions of the Mariana Trench, there is a quiet truth that sits underneath everything. We have barely seen it. Not metaphorically, literally. The vast majority of the trench has never been observed directly by a human or a camera. Maps exist. Data points exist. But vision, the thing we rely on most to understand a place, is almost entirely absent. In that darkness, the possibility of the unknown remains not just plausible, but likely. The trench spans an enormous area, with steep walls, ridges, terraces, and deep pockets that create countless potential habitats. Each variation in shape can influence local conditions. Slight changes in slope, exposure, or material can alter how particles settle, how fluids move, and how organisms interact. Even small differences can matter in an extreme environment. Multiply those differences across the length of the trench, and the number of possible niches grows rapidly. Direct observation is rare because it is expensive, technically demanding, and risky. Cameras can only see what they are pointed at. Vehicles can only visit a handful of locations. Lighting is limited. Visibility is constrained. Every image captured represents an island of certainty, surrounded by an ocean of assumption. Between those islands lie vast stretches of unobserved terrain. History suggests caution here. In other deep-sea environments, new species have often been discovered when observation methods improved or expanded. These discoveries were not always dramatic or exotic. Sometimes they were organisms that had been overlooked because they were small, rare, or behaved in ways that avoided detection. The trench, with its extreme conditions and sparse populations, is an ideal place for such oversight. Unknown species do not have to be bizarre to be important. Even organisms that resemble known groups may function differently, filling ecological roles we have not anticipated. Subtle differences in physiology or behavior can have outsized effects in an environment where resources are limited and interactions are finely balanced. Missing such species means missing pieces of the ecological puzzle. There is also the possibility of entirely unfamiliar ecosystems. Not ecosystems in the sense of lush communities, but systems organized around interactions we do not yet fully understand. Energy pathways, chemical exchanges, and biological relationships could exist that do not map neatly onto familiar frameworks. Without direct observation, these systems remain speculative, but the conditions that might support them are present. Technological limitations amplify this uncertainty. Cameras require light, which can alter behavior or fail to reveal subtle features. Sensors capture specific parameters, not holistic experiences. Even high-resolution imagery can miss what lies just beyond the field of view. The trench environment is three-dimensional, and much of it remains unexplored in all directions. Time also matters. observations capture moments, but some species may be active only occasionally, emerging under specific conditions. Others may be seasonal in ways we do not yet recognize. Rare events may bring organisms together in ways that are invisible during brief visits. Without continuous monitoring, these patterns remain hidden. There is a temptation to assume that what we have seen represents the whole. This is a comforting illusion. It simplifies the narrative. But the trench resists simplification. Its remoteness and difficulty of access ensure that gaps in knowledge persist. These gaps are not small, they are vast. Acknowledging the possibility of unknown life is not speculation for its own sake. It is a recognition of scale and limitation. When observation coverage is minimal, uncertainty is the rational position. The question is not whether unknown species exist, but how many and how significant they are. This uncertainty has implications beyond taxonomy. Understanding biodiversity influences how we think about resilience, adaptation, and the limits of life. The trench may host solutions to survival that challenge existing models. Missing those solutions means missing opportunities to refine our understanding of biology under extreme conditions. The idea that entire ecosystems could remain unseen may feel unsettling, but it is also inspiring. It means discovery is still possible on our own planet, not in distant galaxies, but beneath our oceans. The Mariana Trench remains one of the last places where exploration in the classic sense is still possible. In the end, the darkness of the trench is not just a lack of light, it is a lack of information. Every descent illuminates a small patch of that darkness, revealing detail, complexity, and surprise. But until those patches connect, the possibility of the unknown remains very real. And in science, that possibility is not a weakness. It is an invitation. Evolution is often presented as a tidy process. Variation appears. Selection favors what works. Over time, populations adapt. It is a powerful framework, and it explains an enormous amount about life on Earth. But the Mariana Trench has a way of poking at the edges of this confidence, not by disproving evolution, but by exposing how narrow some of our assumptions have been about what adaptation can look like and how it can unfold. Many evolutionary models are built around environments that change relatively quickly or predictably. Seasons shift, climate fluctuates, resources vary. Organisms respond by adapting traits that improve survival and reproduction under those conditions. The trench, by contrast, is defined by long-term stability in some parameters and extreme constraint in others. Pressure does not fluctuate meaningfully. Darkness is permanent. Food scarcity is chronic. This creates an evolutionary context that does not fit neatly into common narratives about rapid adaptation driven by changing environments. One challenge arises from timescales. Evolutionary change is often inferred from relatively fast-moving systems, where selective pressures shift over generations. In the trench, selective pressures are constant but severe. This raises questions about how much flexibility is possible once an organism is deeply specialized. Adaptation here may favor robustness and persistence over versatility. Traits are not optimized for change, but for endurance. This challenges the idea that adaptability always means flexibility. Another issue is constraint. Traditional models often assume that adaptation can explore a wide range of trait space. In extreme environments, the viable options may be far fewer. Only certain molecular structures, physiological processes, or life strategies may work at all. Evolution in the trench may therefore be less about innovation and more about fine-tuning within very narrow boundaries. This kind of evolution is harder to detect and harder to model because changes may be subtle but crucial. The trench also complicates assumptions about trade-offs. In many environments, adaptations involve balancing competing demands: speed versus strength, growth versus reproduction. In the trench, energy scarcity and physical extremes can collapse these trade-offs. Some traits may be non-negotiable, others may be irrelevant. Evolutionary outcomes may reflect survival thresholds rather than optimization. Life does not choose the best option, it chooses the only option. There is also the question of isolation. Evolutionary theory often emphasizes gene flow, population structure, and connectivity. The trench may limit these processes in ways that are difficult to quantify. Populations may be isolated not by distance, but by depth and pressure barriers. This could lead to divergence driven by physical separation rather than ecological differentiation. Alternatively, unexpected connectivity could exist through pathways we do not yet understand, complicating assumptions about isolation entirely. The role of chance becomes more pronounced in such environments. When populations are small and conditions are extreme, random events can have outsized effects. A single successful adaptation may dominate not because it is optimal, but because it is sufficient. This stochastic element challenges models that rely heavily on deterministic outcomes. Another area of tension involves developmental constraints. Evolution does not start from scratch. It modifies existing structures. In the trench, the starting material matters immensely. Lineages that arrive there with certain pre-adaptations may succeed, while others fail entirely. This historical contingency means that evolutionary outcomes are shaped as much by ancestry as by environment. Models that emphasize environment alone may miss this nuance. The trench also invites questions about evolutionary rates. Does extreme stability slow evolution by reducing selective change? Or does extreme pressure accelerate it by narrowing survival margins? Evidence suggests that neither answer applies universally. Different traits may evolve at different rates within the same organism. Some systems may be frozen in place, while others remain surprisingly dynamic. This mosaic of evolutionary tempos complicates simple narratives. Importantly, trench research highlights how much of evolutionary theory is built on accessible systems. Most data comes from environments we can observe easily. The trench is a reminder that our theories are shaped by what we can study. When new environments are explored, those theories are tested in unexpected ways. Sometimes they hold, sometimes they need adjustment. This does not undermine evolution as a framework, it enriches it. The Mariana Trench expands the range of conditions under which evolution is known to operate. It forces models to accommodate persistence under extreme constraint, adaptation without flexibility, and survival without abundance. In the end, the trench does not overthrow evolutionary theory. It humbles it. It reminds us that life's solutions are not always elegant, not always efficient, and not always intuitive. Evolution does not aim for beauty or simplicity. It aims for continuation. And in the deepest, darkest parts of the ocean, that aim produces outcomes that stretch our understanding and quietly suggest that there is still much to learn about how life truly adapts. For decades, the Mariana Trench was studied mostly from afar. Instruments were dropped, measurements were taken, and conclusions were drawn from indirect evidence. It was a bit like trying to understand a city by listening to echoes in the alleyways. Then technology began to change, and with it, the nature of observation itself. New submersibles and robotic systems did not just add more data. They changed the questions scientists could ask, and exposed how fragile some long-held assumptions really were. Modern submersibles are built with capabilities that earlier designs could not achieve. Improved materials, better pressure resistance, and more reliable power systems allow for longer, deeper, and more controlled missions. Instead of brief descents focused on survival, missions can now emphasize exploration. Vehicles can linger, maneuver precisely, and revisit locations. Time, once the enemy, has become an ally. Robotics has played a particularly transformative role. Autonomous and remotely operated vehicles can perform tasks that were previously impossible or impractical. They can map terrain in high resolution, follow complex paths, and collect targeted samples. Unlike human-occupied vehicles, they do not require life support systems, allowing for greater flexibility in design and deployment. This shift has expanded the spatial and temporal reach of trench research. Perhaps the most significant change is visual clarity. Advances in imaging technology have improved resolution, sensitivity, and coverage. Cameras can capture fine details in low-light conditions. Imaging systems can scan large areas systematically rather than relying on chance encounters. This has revealed seafloor features and biological activity that earlier missions simply missed. These new views have forced revisions of older ideas. Areas once thought to be uniform have turned out to be structurally complex. What appeared as flat expanses are now known to include subtle ridges, depressions, and textures that influence local conditions. These features matter. They affect how materials accumulate, how organisms distribute themselves, and how physical processes operate. Assumptions about scarcity have also been challenged. Earlier observations, limited in scope, suggested that life was sparse and evenly distributed. New surveys show patchiness, clustering, and variation. Some areas host more activity than expected, while others remain relatively barren. This unevenness suggests underlying drivers that were previously invisible. Robotics has also improved sampling precision. Instead of collecting whatever happens to be nearby, modern systems can target specific features or organisms. This reduces uncertainty and improves contextual understanding. Samples can be linked directly to their surroundings, allowing for more accurate interpretation. Older assumptions based on mixed or poorly contextualized samples are now being re-examined. Navigation advances have further refined understanding. High accuracy positioning allows scientists to return to the same locations repeatedly. This enables change detection over time, revealing dynamics that were once assumed to be static. The trench is increasingly seen as an active system, not a frozen snapshot. With these advances come uncomfortable realizations. Some conclusions drawn from earlier data were not wrong in intent, but incomplete or skewed by limitations. Patterns inferred from sparse observations do not always hold when examined in detail. Relationships once thought to be simple turn out to be complex. The trench resists reduction. Importantly, new technology also exposes its own limitations. Better tools reveal more complexity, which in turn demands more nuanced interpretation. High-resolution data can overwhelm existing frameworks. Seeing more does not automatically mean understanding more. Each technological leap creates new challenges alongside new insights. There is also a cultural shift within the science itself. As tools improve, collaboration becomes more essential. Data volumes increase. Expertise must span engineering, biology, geology, and data science. The trench is no longer approached as a single problem, but as a network of interrelated systems. This integrated perspective is a direct result of technological progress. New submersibles and robotics have not solved the mysteries of the Mariana Trench. They have done something more valuable. They have shown how much of what we thought we knew was shaped by what we could see at the time. As vision improves, confidence must be recalibrated. The trench remains deep, dark, and demanding. But it is no longer quite as silent as it once was. Each descent brings sharper images, richer data, and a clearer reminder that understanding is provisional. Technology does not deliver final answers. It reveals better questions. And in the Mariana Trench, those questions are still unfolding, one dive at a time. Uncertainty makes people uncomfortable. It feels like a loose thread, an unfinished sentence, a mistake waiting to be corrected. In science, uncertainty is often misunderstood as weakness, as if admitting what we do not know undermines what we do. The Mariana Trench quietly dismantles that idea. Here, uncertainty is not a flaw in the process. It is the most honest result we can produce when confronting a system that refuses to be simplified. The trench challenges the instinct to tidy reality into clean narratives. It is tempting to frame it as a single extreme environment with a set of defining characteristics. But every new observation complicates that picture. Conditions vary, processes overlap, outcomes diverge. The deeper scientists look, the less satisfying a single explanation becomes. This is not because science is failing, but because the trench is doing what complex systems do best, defying compression. In many fields, uncertainty shrinks over time as data accumulates. Patterns emerge. Models stabilize. In the trench, data accumulation often reveals new layers of variability. Measurements that once seemed precise are placed in broader contexts that expose their limitations. Each answer generates new questions. Instead of converging towards simplicity, understanding fans outward. This pattern can feel frustrating, especially in a culture that values definitive statements. But uncertainty here carries information. It tells us that the system operates across multiple scales, with interactions that cannot be captured by a single metric or model. Physical forces, chemical gradients, biological responses, and geological dynamics intersect in ways that amplify complexity. Uncertainty marks the boundaries where our current tools and concepts stop being sufficient. Importantly, this uncertainty is structured. It is not chaos. It follows from known constraints and observed variability. Scientists can describe what is uncertain, why it is uncertain, and what kinds of data would reduce that uncertainty. This distinction matters. It separates ignorance from informed humility. The trench pushes researchers toward the latter. There is also a human dimension to this process. Scientists are trained to seek clarity, but also to recognize limits. Working in the Mariana Trench requires an unusual level of patience. Progress is slow, results are provisional, revisions are common. This environment rewards those who are comfortable holding multiple hypotheses at once, resisting the urge to declare closure. Public perception often struggles with this. When scientific conclusions change, it is sometimes seen as inconsistency. In reality, it reflects refinement. Early interpretations are updated as new data becomes available. The trench magnifies this dynamic because new data arrives infrequently and often carries disproportionate weight. Each addition can shift understanding noticeably. The idea that uncertainty equals failure collapses under this reality. If scientists only reported what they were certain about, they would say very little about the trench. Instead, they map uncertainty, using it to guide future inquiry. Areas of high uncertainty become priorities for exploration. Gaps in knowledge become targets, not embarrassments. This perspective also reshapes how success is defined. A mission that reveals unexpected variability is not a disappointment. It is a success that expands the known space of possibilities. Discovering that a system is more complex than assumed is a valuable outcome. It prevents premature closure and encourages more nuanced thinking. The Mariana Trench serves as a reminder that nature does not organize itself for our convenience. It does not conform to textbook categories or respect conceptual boundaries. When explanations feel strained or incomplete, it is often because they are. Uncertainty signals that reality is richer than our descriptions. In this sense, the trench is a teacher. It demonstrates that the goal of science is not to eliminate uncertainty entirely, but to understand its structure and implications. Certainty can be comforting, but it can also be misleading if achieved too quickly. Uncertainty keeps inquiry alive. As research continues, some uncertainties will shrink. Others will persist. New ones will emerge. This is not a problem to be solved, but a process to be navigated. The Mariana Trench does not reward confidence. It rewards curiosity, caution, and resilience. Ultimately, embracing uncertainty is not a retreat from knowledge. It is an acknowledgement of depth, both literal and intellectual. The trench is deep in ways that resist flattening. Our explanations must be allowed to deepen with it, even if that means living with unanswered questions a little longer. There is a quiet humility that settles in when thinking about the Mariana Trench. Not the dramatic kind that arrives with awestruck silence, but a slower realization that seeps in over time. After decades of study, advanced technology, and careful analysis, the deepest place on Earth still refuses to be fully understood. It does not push back loudly. It simply continues to exist, unchanged by our conclusions, perfectly comfortable with our uncertainty. The trench stands as a counterpoint to the modern belief that everything important has already been figured out. Satellites map the surface of the planet. Data streams quantify climate, weather, and movement. Algorithms predict patterns. And yet, just beneath the waves, a vast environment remains largely unknown. Not unknown because it is invisible, but because it is difficult. Depth imposes limits that no amount of confidence can override. What makes the Mariana Trench especially humbling is that it is not alien. It is not distant, it is part of Earth. The same planet that supports cities, forests, and skies also hosts an environment so extreme that it bends our expectations. This forces a re-evaluation of what it means to know a place. Proximity does not guarantee familiarity. Accessibility shapes understanding more than location. Throughout this exploration, one theme repeats without repeating itself. Assumptions crack under pressure. Tools struggle. Models stretch. Definitions blur. None of this signals failure. It signals contact with reality at its most demanding. The trench is not an outlier to be explained away. It is a reminder that the planet operates across a range of conditions broader than our everyday experience. There is something almost mischievous about it. Every time a confident statement is made, the trench seems ready to complicate it. Measurements shift, patterns fragment, exceptions appear. It is as if the Earth is gently reminding us that certainty is provisional and that patience is a prerequisite for understanding. This does not diminish science. It elevates it. The willingness to be wrong, to revise, to question, is what allows knowledge to grow. The trench rewards this mindset. It resists final answers, but it yields insight to those willing to listen carefully and adjust expectations. The humor, subtle as it may be, lies in the contrast. We build machines capable of descending into darkness, surviving pressure that defies intuition, and sending back streams of data. And then that data politely refuses to behave. Variables refuse to align neatly. Patterns refuse to repeat exactly. The trench does not sabotage our efforts. It simply refuses to simplify itself for our convenience. There is also comfort in this. A world fully explained would be a smaller one. Mystery creates space for curiosity, for imagination, for discovery. The Mariana Trench preserves that space. It reminds us that exploration is not finished, even on a planet we call home. This perspective has broader implications. If the deepest parts of our own oceans remain only partially understood, what does that say about our relationship with the planet? Knowledge is not ownership. Understanding is not control. The trench exists independently of our interpretations, operating on principles that do not require our approval. And perhaps that is the most valuable lesson. The Earth does not hurry to match our timelines. It does not correct our misconceptions on demand. It allows us to be wrong, sometimes for decades, while quietly holding on to the truth. Progress comes not from forcing answers, but from earning them. As research continues, the trench will slowly become less mysterious, but it will never become simple. Each layer of understanding will reveal another beneath it. Depth, after all, is not just a measure of distance. It is a measure of complexity. In the end, the Mariana Trench stands as a reminder that certainty has limits, and that those limits are not flaws. They are invitations. Invitations to keep asking, keep exploring, and keep accepting that the planet is under no obligation to make itself easy to understand. The deepest place on Earth does not demand reverence. It demands humility. And it seems perfectly content knowing that, for a while longer, it will continue to outthink us, outweight us, and quietly remind us that mystery is not a problem to be solved, but a reality to be respected.